Okay, so let's resume actually. So before we get into the
Is it possible that a beta hat may lie inside the square or the circle?
Okay, let's see. So your question is?
Beta hat
Yeah.
that is outside the region.
Yeah.
So is it possible that it lies inside the square?
Yes. Good point. So the question is, why did I draw beta hat outside this diamond or the circle over there? Okay. So that was only for illustration. The beta hat can belong to the region. I mean, could be either outside or inside. We drew the one, the choice where it was outside. If it is inside, that is going to be the best model. Okay, because it satisfies the constraint and it is the one which minimizes the residual sum of squares. So that's the best model. Okay. So, but how do you get, like, let's say beta is right there, you can't change it. Then how do you get, you can expand this region by increasing the t, right? Increasing the t is essentially bringing the lambda close to 0. And in the limit, not in the limit, but like if you really set lambda to be 0, then that's not there. Then beta hat is the best choice. Yeah, that's the intuition. Yeah, good question. So before we get to the maximum likelihood version, so there is this really cool, I guess, mind map. That's what these are called for machine learning. So I have shared the link, I think, on the syllabus page. I don't know where the syllabus page is. So okay. Yeah. So the third link here is essentially this PDF. It'll get you to the PDF. So the PDF is essentially giving you some idea of like what's happening in the. So what are different things that you can consider? Like for example, in terms of features, what are some things are too exotic, but like feature encoding, how do you not importance, but feature selection, for example, right? Subset selection was a way to do feature selection, but there are different other things that you can compute across features and so on. So this is the first I guess page of this PDF. What is this? So concepts, so approaches that we are currently looking at. We are essentially looking at something, just linear models. It's not even there, but performance analysis. So here we have seen mean square error, which is essentially what I'm calling as the residual sum of squares, right? That's what this is, and this was the 0-1 loss or the misclassification error for classification. But we'll see this error next time. I mean this guy next time, okay? And methods. Cross validation has so many variations, but we saw one variation here. So if you look at this, okay, there's leave p out, leave one out, k-fold cross validation. K-fold cross validation is the version that we saw here. Leave one out is another interesting cross validation technique, but there are many others. Okay, so you should, you don't have to know them exactly, but you should at least look at what we discuss in the class on this map. Okay. Yeah, we'll see several of these things actually, like what is meant by bagging, what is bootstrap later on. What's happening in the next? So there are 5 such slides or 5 such pages. So yeah, the process basically. So here there is, just try to understand what's happening in each slide, each page. I think in the next one they have the mathematics, but it just means, notation to talk about things like, what is a variance, what is a covariance, what is the correlation. Okay, these are things that you should know from probability refresher and so on, but they have introduced it again here. So just use it. If you're feeling lost, then definitely this is a good thing to get a bird's eye view of what you're doing. Okay. In the notes there is actually example which is essentially from this website, Stack Overflow. How many of you use Stack Overflow to see your R questions? Okay. Can you imagine if Stack Overflow is not there? How difficult life would be. But you can actually get the data dump from Stack Overflow if you are concerned that it will not be there tomorrow. But so they have this nice feature that they added to their website called salary calculator. Okay, so actual calculator looks like this, and they're asking us to take survey for 2019 to create a calculator. So here actually you can select a role that you want, maybe a data scientist, let's say masters. There's a couple of years of experience, technology, R. Let's see if I just know R, how much would be the salary. So it's just a interesting thing. They're just taking some data points. That those data points are your features. Some of them are categorical, some of them are ordinal. There is an order relationship between experience, right? Experience of 2 years and experience of 3 years. There is an order relationship, and they are discrete. Okay. So given that's a feature vector, whatever I filled in the last page, given that feature vector, which has location as well, location is a categorical feature. Given that, they are producing, I guess, median and a couple of other percentiles. So these can be a Y value. So you could have multiple outputs. Okay. Essentially, this is a representation of the conditional probability of Y given X. Given X was what I did in the previous slide, previous page, right? Given that X, this is the conditional probability with 25th percentile, 50th percentile, and 75th percentile. They're not showing the conditional probability of Y. Y is a number, a positive number, it represents dollars, right? But they're not drawing that probability distribution. It could be, it could look like a normal distribution or not, but they're just showing you what the percentile values are. And it will not be a normal distribution. In fact, salaries, it turns out, have look like a log normal distribution. Okay, what is a log normal distribution? A log normal distribution is if Y is a log normal random variable, then the log of it is a normal random variable. Okay, that's it. So if Y is log normal, then log of Y is normal. Okay, so it turns out that if you plot the histogram of all salaries, they saw that it was not looking like a normal distribution. Okay, it was not looking symmetric or bell shaped. Anyway, salaries have to be greater than 0. So it was looking in a certain shape, and they assumed that it's log normal. So they did a log transformation of the output. Okay, so these are tricks that you can also do for your data sets. You can transform input features. You can also transform output features. So you can also transform dependent variable. Okay, you can change it to a log scale. You can square it and so on. Whatever it's basically driven by prior knowledge or intuition. So there's a brief description about this particular, I guess, exercise. They essentially do linear regression here. So you can look at what they did on this blog post, which is linked on the notes. Okay. Any questions about this? I've not really gone into details of what they did, but you should play around with this. Essentially, that's a web app, right? So you learn linear regression. They made a web app out of it. So that's cool. Any questions so far? Okay, so then let's get back to this. Okay. So this was a geometric view, but now what we're going to do is look at likelihood view, and for that we'll have to recollect Bayes rule. Okay, we'll start with Bayes rule and talk about what is meant by maximum likelihood estimation for a couple of minutes. So this should be familiar to all of you. If you think of two events, okay, event B given event A is the probability of B and A, okay, actually intersection, let's say, divided by probability of A. Okay, right? This is just a definition of a conditional probability. Conditional probability of the event B happening given A has happened is the probability that both of them happening. Both the outcomes in B and A happening divided by the probability that outcomes in A are happening, right? So there's a random variable version of this, which is the probability of random variable Z given W is equal to probability of Z and W divided by probability of W, right? So this actually hides a lot of information. It's actually just saying probability of z is equal to little z given w is equal to little w. You know this, right? So w is equal to little w and z is equal to little z divided by probability of w is equal to little w. That's what the thing on the top means. Okay, it's just a short form for what we wrote. So this is just a definition of conditional probability of events or random variables. Okay, random variables, just think of this version. Now what is Bayes' rule is essentially like I could have done this right, probability of let's use the random variable version, z given w times probability of w is a joint probability of z and w, right? That's the thing on the top right. Then I can just write that as joint probability of z and w is the probability of w given z times probability of z. Okay, all I'm saying is this is equal to probability of z and w. I mean, so this is just follows from this equation. So I just brought the denominator to the left hand side, then I got this guy is equal to this guy, right? That's what if I bring the denominator to the left hand side means. And then I'm just saying that whether if you look at the conditional probability of w given z, that is also the probability of z comma w divided by probability of z. Okay, that's how you get the Bayes rule. So from here, the Bayes rule is essentially probability of z given w, let's say, is equal to probability of w given z times probability of z divided by probability of w. Okay, I just brought the term over here, this guy, to the denominator. Okay, in the central, this equation. So this is Bayes rule. Okay, it's just called Bayes rule. But what is this interpretation? The interpretation is as follows. Okay, so who's not comfortable with this notation so far? Who's is everybody fine with the notation? Am I going too slow? Okay, it's fine, right? Okay, so this is Bayes rule. What is the interpretation of each term? So P of z is called a prior. Okay, I mean, I can always switch z and w. Okay, for let's assume that z is the guy which is on the left hand side with just z itself in the numerator. So probability of z is called the prior. Probability of w given z is called the likelihood. Okay, whenever somebody says a likelihood, it's just a conditional probability. It's just a conditional probability. Okay, so whenever people use likelihood in English, they almost certainly just mean conditional probability of something, or conditional probability of w given z. Okay, in this case. And the thing on the left hand side is called the posterior. Okay, is the posterior probability of z given w. Okay, so what is Bayes rule relating to? They are asking the question. Okay, there are two random variables. Think of w as data. Okay, something like data, evidence. So they're asking, what is my posterior probability of z given that I've seen something? That's what a conditional probability even means, right? Probability of something given that something has happened. Okay, they're saying that posterior probability of z is actually just the prior probability of z times some multiplication. Okay, this times a multiplication, which is just the likelihood of the data or likelihood of w given z divided by the marginal probability of w itself. Okay, so denominator, let's not worry about it. Let's understand that so given that w has happened, I just want to revise my probability distribution over z. Okay, think of z as a Bernoulli random variable. It's a coin flip. Let's say my prior was that it's a unbiased coin flip. Sorry, it's an unbiased coin, which means that my probability of z is equal to 1 is the same as probability of z is equal to 0. It's 1/2. Okay, it will land heads 1/2, lands tails 1/2. Now let's say w is a number of heads in 100 trials. Okay, it's like think of that as a binomial random variable. Okay, so probability of w given z is the likelihood of seeing some number of heads given that z is a z corresponds to the bias of the fair coin. Okay, So given that the coin is fair, okay, what is the probability that given the coin is fair, I'll observe 50 heads? It's pretty high. Probability that it's 90 heads, pretty low, right? Given that it's fair coin, I should not see, I should probably see something closer to 50 rather than 90 instead of 100. Close, for 100 trials, 100 flips of the coin. Now, the left-hander is saying, given that you saw some number of heads, right? Maybe 50 heads, maybe maybe 100 heads, maybe 90 heads. Now, tell me the revised probability. Tell me the revised bias of your coin, essentially. Okay. You initially thought it was fair. You saw some, there was a likelihood of something, likelihood of certain heads happening given that it was fair. But now tell me that I've already shown you that there were maybe 70 heads or 90 heads. Tell me a revised number for what the bias of the coin is. Okay. That's just the English intuition. I have not really grounded it in these random variables, so take it with a pinch of salt. But that's the intuition. Okay. Any questions here? Okay, so that's base rule, and we're gonna think of a beta. Okay, so I'm gonna relate it to LASSO and what is the other thing? Ridge regression, using the notion of a likelihood and a prior. And so for me, I'm estimating beta, right? So my data, I'm getting beta, right? So I'm going to make beta a random variable. This is a big leap here, which we did not see so far in the past 3 lectures. Now beta is going to be a random variable. That's crazy, right? I mean, it's a p-dimensional vector. Now I'm saying it's a random variable. Okay. That's a big leap. So let's assume that that's true. Okay. Let's assume that is true. It is a random variable. Then my prior, let's say, is that beta is normally distributed with mean 0 and some variance. Okay. What do I mean by that? So beta, let's pick that example, right? Beta is beta 1, beta 2. Think of 2 dimensions. So I'm saying that this is normally distributed with mean 0 and some variance, and I'm just going to use some variance. So sigma square 0 0 sigma square, let's say. I mean, this has to be a 2 cross 2 matrix because it's 2 coordinates. It's a 2 coordinates. Each coordinate is also normal anyway, but it's a 2-dimensional Gaussian. Think of a bell type of a inverted bell thing in 2 dimensions. Okay, that's this guy. So I'm going to assume that beta is normal initially. Okay, that's my prior. Now my likelihood model is going to be that y given beta, let's say x's are fixed. Okay. Okay. So given beta and x, essentially, so I don't want to bring randomness into x. Let's say x is fixed, x is not random. Then y given beta, I'm also saying that let's say this is also normal. Okay. So I'm using n for normal or Gaussian distribution, and so I'm going to assume that its mean is beta transpose x. Okay, and some variance. Since y, let's say y is one dependent variable, 1-dimensional, I'm predicting, let's say, your income. Then it has its own variance. Let's call it tau square. Okay, just some number. I mean, so that symbol is again a Greek symbol. It's just tau square, but I could have used a square, b square, c square, some variance. Okay, instead of sigma, because sigma I already used over there. Okay, so I'm just saying that given beta, this is the conditional probability of y given beta. I'm just saying that the conditional probability of y given beta is also normally distributed. The mean depends on beta. So of course, condition on a certain beta, then the mean is going to be something like this. This is my assumption. Okay, in the sense I'm assuming that beta is random variable. It has a prior. There's a likelihood of me observing y given beta is like this. Then the posterior beta given okay, let me not write the posterior first, let me write the okay. So if this is a likelihood, then the probability of me observing, think of y1 is equal to little y1, y2 is equal to little y2. Let's say I have n data points, yn is equal to little yn. I have n observations, right? I'm just saying that I observed these n guys. The probability of me observing these specific n values is nothing but the product, and for product people use the big capital pi notation. It just means a product. Okay, it's a product. What is it a product of? Normal distribution. So product of I is equal to 1 to n of 1 by square root 2 pi tau e to the power minus yi minus beta transpose xi the whole square divided by 2 tau square. This is just a definition of a normal PDF, right? So this part is the definition of the normal PDF. I'm just saying that if my x feature is little xi, and given that I have told you, given the beta, the mean is beta transpose xi, and y taking a value little yi is yi minus the mean, the whole square, divided by 2 sigma square, and in this case instead of sigma I'm using tau because I already used sigma somewhere else. So this is the likelihood. This is the likelihood of the data. Actually, given beta, I should given beta and x's, for example, xi's, whatever. It's not well written, but I just think of it as given beta. It's the same as this, but this was written for a generic y and x, and I just wrote for my given data. This is literally the likelihood. Okay, this is the likelihood of me observing the data given a specific beta. Okay. So given this, I can find the posterior probability of beta given data, which is that given y1 is equal to little y1, y2 is equal to little y2, all the way to yn is equal to little yn. Okay, I can find this. This is called the posterior distribution on beta, and there's no special magic. I'm not gonna laboriously do it, but this guy, see, I just defined the likelihood. I just defined the prior. I mean, we can write it in a PDF form like this. Given that, you can write the posterior. Okay, the posterior is just gonna follow the base rule. This base rule. I just told you what this term is, that term is. Denominator I did not tell you, but it's something you can. It's not very critical. Given that, you can write the posterior. Okay. It turns out that the posterior is also normal. Okay. It's not a very important, it's not very important for our discussion, but I'm just saying that if the prior is a normal distribution and the likelihood is also conditional probability, which is the likelihood, is also normal distribution, then product of normal distributions becomes normal. Okay. So why did I write all this? Is to motivate. Okay, I just flipped the slide, but I wrote this to kind of motivate ridge regression. Okay, so remember what was ridge regression doing? Okay, so let me just recall what ridge regression doing and get back to the likelihood part. So ridge regression is minimizing sum over I is equal to 1 to n of yi minus beta transpose xi square. This is the residual sum of squares plus some lambda times sum over I is equal to 1 to p beta j square. I mean, let's say j here. Yeah. So this was the ridge regression. So ridge regression problem was minimizing this over betas, right? Okay. So if you have the base rule, which is the posterior probability of beta given, let me just call it data. Data just means yi is equal to little yi for all I. Okay. Uh, it's proportional to. Proportional to, people use this crazy symbol where they don't have the something towards the right end, but it's like a infinity symbol without something chopped off towards the right side. Okay, that thing. It's proportional to probability of data given beta times probability of beta. And we saw this. This was normal. This was a product of normals. We saw this. I just put proportional to because I forgot about the denominator. Denominator doesn't depend on beta actually. Okay, so this was the Bayesian point of view. There's a distribution associated with beta here, but what I want to actually do is, now I don't want to think of distribution or beta because that seems like crazy. Like for every beta vector model, I have a probability mass. So let's not. So what I want to do is now think of what is called maximum a posteriori estimate. Okay, it's a mouthful, but all it just means is I want to find. I know that posterior I can just compute with Bayes rule, but I don't really want the whole posterior because it looks like a complicated object. So I just want the maximum of that posterior. Okay. Posterior is a distribution. Think of it as a normal distribution. I just want to find where does it achieve its max. And it achieves its max for a normal distribution. We know it achieves its max at the mean, but in general it can be anything. There's a distribution, some curve like this, and we want to find the max. Okay. So that MAP estimate is essentially maximizing the posterior. This is the posterior. Essentially maximizing over beta of probability of data given beta times probability of beta. Okay, and instead of this, let me do a simple trick. Okay, and I'll take a log of the objective. That will give me log probability of data given beta plus log of the probability of beta. Okay, I just took a log transformation. Why is it, why doesn't, why can I do this? Is because log is like an increasing function. Okay, probability numbers are all positive. Let's say they are positive. I mean, they are positive, but let's say they are not 0. Okay, then log is well defined. Okay, and log doesn't change where the maxima occurs. Okay, that's a fact that let's not get into. I can do this. Okay, and this guy, log of probability of beta, I assume beta to be normal, right? Here, beta is normal distributed, this guy, right? Then the log of the probability of beta, let me just expand log of the probability of beta. The other term we'll see that we'll just assume that that's true. So log of probability of beta is going to be log of 1 by square root 2 pi sigma, okay, e to the power in this case it's going to be a bit messy, but let's say minus 1 by 2 sigma square, okay, beta 1 square plus beta 2 square. Okay. Because it was a normal distribution with mean 0 and covariance being sigma square and sigma square, it's as if saying I have two independent Gaussians, two independent normal distributions, because there is no correlation correlation between them. So because the off diagonal elements are 0, so there is no correlation between them, like here, right? So all I'm saying is think of beta 1 and beta 2 as separately Gaussian. That means that the probability of beta is just the probability of the first coordinate being Gaussian times probability of second coordinate being Gaussian. That's essentially, okay, maybe there's a, no, this is, okay, maybe there's a square here, let's say. So the log of the probability of beta is something like this. Okay, are people fine with this? I'm just, so you don't have to work through the formula, but I just substitute the probability of beta to be a product of Gaussians. Okay, now this guy is essentially like sum of j is equal to 1 to p of beta j square. There are only two betas, beta 1 and beta 2, sorry. So that's this guy. Okay, so maximizing, actually there's a negative sign here, so think of Okay. Okay, there's a, I don't know where to introduce. Okay, so let me not put max here. Minimize the negative log and the negative log. Okay. So maximizing some objective is the same as minimizing the negative of the objective. So I like this version. Okay, because then I can think of a negative sign here. This whole term. This whole term is the negative of the log of something which is a Gaussian distribution. Okay, and that's exactly, I mean, with some additional factors, but which don't depend on beta. So this is essentially this term, which is somehow j is equal to 1 to p beta j square with some lambda in the front. Okay, and the lambda is going to be because of this 1 by square root 2 pi sigma square, all that stuff. I'm just saying there's a multiplicative factor, so that's lambda. Think of that as lambda. I mean, we can figure out exactly what this lambda is, but that's beside the point. So I'm just saying that if you maximize, if you do Bayes rule, find the beta with the highest probability mass, that's the maximum a posteriori estimation. That essentially is solving this maximization problem, or trying to find that beta which maximizes these probability times probability, likelihood times prior. That's the same as minimizing the negative log of the likelihood times the prior. Okay, then and log of a times b is log of a plus log of b. So that's why there's a minus log of a minus log of b with a minimization in the front. I'm just saying that the second term is equal to lambda times sum over j is equal to 1 to p of beta j square. Okay, now you can imagine the first term is going to be that. What do I mean? The first term, negative log of the probability of data given beta, is essentially residual sum of squares of beta. All I'm saying is sum of I is equal to 1 to n yi minus beta transpose xi, the whole square, is proportional to negative log of, I guess this negative log of probability of data given beta. Okay, and this we saw. I mean, I don't want to rewrite it, but I can rewrite it. Do you guys want me to rewrite it, or it's basically we just saw this here, right? This is the probability of. So I just call this thing inside data. Okay, that's what the data is, right? Little yi. I just said x is a fix. That's why x's are not random here. But other than that, everything is, this is data. So data given beta is the likelihood, is this term. If you think of, if you take the log, forget about the product, forget about this coefficient. Log of e to the power something is what? The something in the power, right? And something in the power has a negation in the front, and I said negative log. So the two negatives cancel, and the term in the power is essentially this. Okay. How many of you are lost at this point? Okay, a lot of you are lost here at this point. Okay, so I had a few things to cover. Okay, so let's actually understand this. Okay, so I wanted to cover interpretation of ridge regression using PCA. I will do that next time. Okay. Before that, let's understand this likelihood business, because it's kind of this is like a hammer that you can use for all models. Almost all models have some good interpretation like this. So let's understand this. So let me start from a different point of view. So whatever we did so far, let's pause it. I mean, it is all correct, okay, and we will use it. But I'll relate residual sum of squares of beta, which is the same as above, right? That's residual sum of squares. Minimizing residual sum of squares is the same as maximizing likelihood. Okay, where there is no okay, maximizing likelihood. What is this likelihood? Is essentially this guy. Okay, the guy inside, the guy underlined. The log and the negative part is just a additional thing. It's just saying, okay, if I add a log and a negative part, it's the same as saying minimizing the negative log of the likelihood. Okay, So why am I calling that the likelihood? Because there is something on the left side, it's conditioned on beta, right? So minimizing residual sum of squares is the same as maximizing likelihood. And what is that likelihood? The likelihood we saw, right? So let me actually expand this out. Minus log of the probability of data given beta is minus log of probability of y1 is equal to little y1 given beta times probability of y2 is equal to little y2 given beta times probability of yn is equal to little yn given beta. Okay, that is my data, right? So given the model, me getting the first observation has nothing to do with me getting the second observation. First observation taking a value little y1 has nothing to do with the second observation taking a value little y2. All I'm saying is the data is independent across observations. So probability of data given beta is the probability of the first observation realizing to some value y1 times the probability of second observation realizing to some value y2 times the probability of the observation realizing to some value yn. So there is n such products here. Okay, is this step fine? Who's not understanding this step? Okay, so then I'll use the fact that log of a times b is log of a plus log of b. Okay, log of 10 times 20. So what is this log? Log to the base e. Okay, so whenever I use log, it doesn't really matter. Maybe in other classes it mattered which base, whether it's base 2, base e, or base 10. Here it really doesn't matter. Let's think of base e. Okay, log of two inputs, let's say log of 10 times 20 is log of 10 plus log of 20. Okay, this is just a fact. And we see here it's a log of a bunch of products here, right? This is times, there's a times here. So you can naturally think that this thing, negative log, is going to be minus log of probability of y1 is equal to little y1 given beta, negative log probability of y2 is equal to little y2 given beta, and so on. There are n such terms. Okay, there is nothing but sum over I is equal to 1 to n, negative log of probability of yi is equal to little yi given beta. Okay, just see this, minus log of bunch of products, use this rule and you will get this. Okay, and let's just focus on this guy. So what is the probability of yi is equal to little yi given beta? We just saw this we assume to be normally distributed, right? So if you remember, we said y given beta or yi given beta the same as is normally distributed with beta transpose xi with some variance tau square. Okay, so let's just substitute that, right? So probability of yi is equal to this is 1 by square root 2 pi tau e to the power minus yi minus beta transpose xi the whole square divided by 2 tau square, right? This is just a definition of a normal distribution. I just said that circular thing is that in our assumption. Everybody is following at this point? Any questions? Who is not following? It's fine. Raise your hand. Okay. What I want to establish now, I just said pause it for now because I was, so above this slide I was trying to show what is called maximum a posteriori estimation, which involved Bayes rule, and I was just showing that LASSO's objective is the same as maximizing Bayes rules, posterior. That's what I wanted to show. Okay, but even before that, I want to show that residual sum of squares, minimizing residual sum of squares, is the same as maximizing likelihood. Okay, it's not even, forget about Bayes rule. I'm just saying that residual sum of squares minimization is the same as maximizing likelihood. Maximizing likelihood is the same as minimizing the negative log likelihood. Okay, why did I bringing in a log? It seems it seems like it's messing up with the objective, but it's not. And the negative sign is because if I maximize something, is the same as minimizing the negative part. Okay, so that's fine. And I'm saying what is the likelihood? Likelihood is the probability of data given beta, We saw what the definition of likelihood was, right? Now data, I have n parts of the data, n observations. I'm just saying that the data, each observation has nothing to do with the other observations, which means that the probability of the first data point is equal to little yi, has nothing to do with the second data point is equal to little y2, little y2 as well. Okay, so the probability of data just splits across probability of each observation. Okay, with a negative log the same as before, the negative log over there. And I said, okay, negative log of a bunch of products, bunch of numbers, a times b times c times d is just going to be a sum. And that's what I said. That's what I did here. It's going to be a sum of n terms of the negative log of each probability. Okay, and each probability is the normal distribution we assumed 3 pages ago. And if you now look at this, what is the log? So what is the log of this guy? What is the log of this term? Is log of 1 by square root 2 pi tau, right? Again, you apply this is a and this is b, right? Plus, so log of e to the power minus something is minus yi minus beta transpose xi the whole square by 2 tau square, right? So log of the term in a circle is log of 1 by square root 2 pi tau minus that thing in the exponent of that probability distribution. Okay. Now you see there is also a negative term in the front here, right? So this guy you can ignore because that doesn't even depend on beta. So that's why I'm just saying that this, let me just put proportionality sign, is the same as sum over I is equal to 1 to n of yi minus beta transpose xi the whole square divided by 2 tau square. Right? I just dropped that constant because it depends on tau, but it doesn't depend on beta. Right? Now this is nothing but your residual sum of squares objective. That's all I wanted to establish, that minimizing, residual sum of squares is essentially taking a log of the likelihood where the likelihood is Gaussian distribution. If you have a Gaussian distribution, taking its log will get you only the exponent. Negative terms will cancel because exponent has a negative part. If you cancel the negative term, that exponent is essentially the same as residual sum of squares. That's essentially what I'm trying to show. Yes, just works. So the question was, does it only work under Gaussian distribution assumption? Yes. This whole, we just assumed 2-3 pages ago that the prior was Gaussian and the likelihood was Gaussian. Prior is not needed for this discussion because we're not even talking about any distribution for beta, but the likelihood has to be Gaussian. Okay. If it only if it is Gaussian, then you can get this nice exponent, and so log and exponents cancel, and therefore you get a squared term, and the squared loss per observation is essentially coming from this viewpoint. If you assume that the data is Gaussian given beta, then maximizing likelihood of the data is essentially the same as minimizing the residual sum of squares. That's the key point. Okay.
This is similar to I think in the earlier class we talked about classification based decision boundary, right? Is it similar to this one?
No, I'm just interpreting residual sum of squares with respect to a likelihood model. That's all. It's not related to base decision boundary.
No, similar, I mean to say, because here also we are trying to get some sort of base information, right?
No. So let's talk about this offline. Don't confuse people. All I'm trying to say is that, okay, we pulled out residual sum of squares as a good scoring function, right? Just do the y minus beta transpose xi, square it. I'm just saying that this is a way to motivate why we got that squared loss. Squared loss is because the exponent of a Gaussian distribution has a squared loss essentially sitting there. So if you take a log and a negative part, then the squared loss just comes into the, gets rid of the log and the exponent, so you get that. Okay. So if you understand this likelihood, that RSS is equal to likelihood, then the map estimation essentially has an additional posterior term. So the negative log of the posterior, if the posterior is also Gaussian, the negative log of that is essentially the ridge penalty, beta square, sum of beta I squares, okay, because it's zero mean. Okay, and in the next class we'll see if we can interpret ridge regression using principal component analysis. Yeah.